It's a real pleasure for me to be here. When I was a visitor to the program 4 years ago, I was very new to this research area, and over these 4 years I learned a lot of very interesting and exciting mathematics from very many people in this room, and I want to say thank you. And especially I want to thank my collaborators, Sakai-san and Takenawa-san, for teaching me a lot about Painlevé equations and about geometry of Painlevé equations. And I also want to acknowledge that I think Takenawa-san was really the driving force behind this project. Okay, so I will talk about discrete Schlesinger transformations and their relationship to different Painlevé equations. And it's a very appropriate place to talk about this because this whole project started 4 years ago here in many ways. And so far, we have the following. We describe something that we interpret as a discrete Hamiltonian function of elementary Schlesinger transformations of Fuchsian systems. And we actually have an explicit formula for the Hamiltonian in terms of coordinates on something that we call decomposition space or eigenvector parameterization of a Fuchsian system. And we use this function to explicitly compute an example of a discrete Painlevé equation of type A2 from the Schlesinger transformation of the Fuchsian system. And this is a partial answer to the problem posted in a paper of Sakai, where there were some examples of different Painlevé equations that don't correspond to continuous Painlevé equations. And the question was to represent them as Schlesinger transformations. So we did one of those 3 cases. And also, when we compared the equations that we get with the sort of a nice and simple form of the equation of this type, we extensively employed the geometry of the space of initial conditions to study the 2 equations, and in particular to find how to change from our coordinates, which were sort of arbitrary, to a different set of coordinates where it's possible to compare the 2 equations. And so that's my plan, to talk about these 3 things. Okay. So, and part of the motivation for this work is to see whether we can find sort of a way to study discrete Painlevé equations using isomonodromic approach and move from second-order equations to higher-order analogs, and maybe do classification of such equations based off the classification scheme for Fuchsian systems, for example, as done in work by Ashima using the notion of a spectral type. And recently, Sakai and his collaborators did this for the order 4 Painlevé type equations in the continuous case. Maybe the same can be done in the discrete case. Okay, so very briefly, there are a lot of similarities between differential Painlevé equations and difference Painlevé equations, and our work is sort of sitting in this corner. We are interested in finding the parallel description of isomonodromic approach and also in Hamiltonian approach. Okay, and the context for Sakai's problem that I mentioned is if we look at the degeneration scheme of Painlevé equations, and this scheme is based not on the surface type of the equation, but rather the corresponding symmetry type, we have elliptic and then multiplicative and difference equations. So here we have the differential part of the diagram, and if you look at the symmetry type, then this is, we computed the following 2 examples, and we're now working on this example. And there's, in some sense, the answer to this question was given in the paper by Bolch, who described the type of a Fuchsian system that you should choose to get this type of symmetry. And I will talk about this example and explain this notation a little bit later on. But to begin with, let me talk about Fuchsian systems. So Fuchsian system, just a matrix system of linear differential equations that has simple poles at some points ui. And these are finite points, and this system may or may not have a pole at infinity. depending on whether this matrix is 0 or not, and we usually assume that, yes, we do have a pole at infinity, and use this point for normalization purposes. And when we look at such systems, we want to sort of distinguish between some parameters of the system that either don't change or change in a predictable way when we study the dynamics, and the actual coordinates on some phase space of the isomonodromic deformations that we consider. In particular, poles of the system we think about as parameters, and as I said, one of them we put at infinity, the other two we can put at 0 and 1 using the Möbius transformation of the underlying Riemann sphere. And so, if we fix the poles, then we can really identify our Fuchsian system with these residue matrices at those poles. And A infinity, although redundant because it's a sum of those matrices with a negative sign, it's convenient to use for normalizing and sort of, say, diagonalize this matrix and reduce the size of the conjugation action by the global gauge group. So we will usually assume that it's diagonal. And that's the first set of parameters. And these parameters UI are used to define Schlesinger deformations. And the second set of parameters consist of the eigenvalues of these residue matrices. And these are the parameters that we would use for Schlesinger transformations, for discrete transformations. And the whole dynamics would be sort of on the fiber of the eigenvalue map. We fix all these parameters and sort of look at what's left to construct the matrices AI, and still need to get rid of some redundancies. Okay, so the spectral type of a Fuchsian system, we take our matrix and we look at the multiplicities or degeneracy of eigenvalues of a matrix and encode it by a partition of the size of a matrix into this non-increasing sequence of integers. And we can always, using some scalar gauge transformation, zero out one of these eigenvalues by essentially moving it to the point at infinity. So we always do that for the highest multiplicity eigenvalue. And then sort of we record these integers for all matrices, and that's the spectral type that is used in the work of Ashima to classify Fuchsian systems. Then we make an assumption that our matrix has a full set of eigenvectors. So even though we allow multiplicities for eigenvectors, we still require that we have actual eigenvectors and not generalized eigenvectors. Then if we construct two matrices of column eigenvectors and row eigenvectors, or right and left eigenvectors, here the dagger means that this is a row eigenvector, we can decompose our matrix into the product of matrices B and C dagger. And this is essentially what we use to parameterize the system. So we introduce the space of all such pairs, call it decomposition space, and this space can be equipped with the standard symplectic structure where vectors B and C are dual to one another. And so now let me try to sort of put everything together. So I start with a spectral type, and I fix this matrix A infinity, and usually we assume it to be the diagonal matrix. And then we pick up a collection of all possible eigenvalues that satisfy the spectral type requirement. And then there is a map from this decomposition space to a Fuchsian system, and we look at the subspace there that has this given eigenvalues and also satisfies an additional condition called the Fuchs relation. So we get something like this. This is a set of all possible thetas. This is the subset that satisfies the Fuchs relation. And out of that, we look at all possible Fuchsian systems that have these eigenvalues and A infinity. And above it, we have the corresponding subset of decomposition space that sort of reduces to the Fuchsian system, and doing various conjugation action to remove redundancies, we end up with a space of accessory parameters, and this is essentially where our dynamics takes place. This is a non-trivial procedure, And really, we're working here, but then we need to do some reduction to get there. Okay, so that's a setup. And now we can look at isomonodromy deformations. As I said, they come in two flavors. The continuous one, where in addition to the Fuchsian system, we also deform the location of the poles, and Schlesinger equations describe the condition where we do this deformation without changing the monodromy of the system. And I'm not going to explain what the monodromy is. Most of the people here, of course, know it. And if not, it's just some prescribed way to deform the system. So this is continuous Schlesinger equations. And in parallel, you can look at discrete transformations where you shift theta by integral shift, and you end up with sort of the following. So you take the matrix Y of the system, and you do sort of a gauge transformation by multiplying it by some special rational matrix function. Then you get the following compatibility condition. And the matrix function has to be chosen in a particular way based off the matrix A of our system. So in other words, what I have here is a Lax pair representation of continuous deformations and compatibility conditions, and the same for discrete. Okay. So Hamiltonian description for Schlesinger equations in terms of the coordinates of the decomposition space goes back to the work of Jimba, Miwa, Mori, and Sato in 1980, and it has the following form. So you see it's just a regular Hamiltonian equations with respect to the symplectic form, and the Hamiltonian is given by the following formula. So here I'm looking at the flows in the J direction where we deform the location of the Jth pole. In particular, if you look at the Fuchsian system of the spectral type this, so now I need to explain this notation. So here we have 4 expressions like this, which means that we have 4 poles in the system, and 2 means that this is a 2 by 2 system. So this is a 2 by 2 Fuchsian system with 3 finite poles and 1 infinite pole. Oops, sorry. And so if we use Mobius transformations to have 1 is infinity, 0, and 1, there is 1 free parameter, and that's a variable t in Painlevé 6. And then, sorry, this Hamiltonian of Jimba, Miwa, Mori, Sato actually reduces to the Hamiltonian of P6. And this is what we've done. We constructed the analog of this for Schlesinger transformations. In particular, we considered something that we call elementary Schlesinger transformation, where we pick up 2 points, and we pick up 2 eigenvalues and eigenvectors at those points. So here, alpha and beta is a location of singular points, and mu and nu is the index of the eigenvector that we use to build up the transformation. And the transformation decreases one of these eigenvalues by 1 and increases the other one by 1. We always need to do integer shifts to get isomonodromy, because there is a factor of e to the 2 pi I something, and with integer that doesn't contribute. And in view of the Fuchsian relation, if we decrease something, we have to increase something else. So that is sort of the simplest transformation we can look at. Then, if we make this choice, this multiplier matrix that defines this elementary Schlesinger transformation is given by the following formula. It's an identity matrix and some rank 1 term. In front of it, you can see it's x minus u alpha, that's where the pole is, and u alpha minus u beta, that's sort of where the 0 of the determinant of this matrix is. And that's how we build the rank 1 part. And then there is an explicit formula for the function h plus that can be interpreted as a discrete Hamiltonian function for the Schlesinger transformation dynamics, and we get equations that are discrete Hamiltonian equations, again in the coordinates b and c, only this time around we need to sort of separate them, and if we choose b as our coordinates, we need to choose the coordinates at the next point, or c bar, for the complementary set. I'm not going to explain why this is the discrete Hamiltonian, but maybe just say a few words. So what you can do is, in the discrete dynamics, you can still look at the action principle and get Euler-Lagrange equation, and then by doing a Legendre transform, get the Hamiltonian version of it, and then you get these equations. And it's not a typo. There is no minus sign in this case. Yes, it is. Yeah. And here's the formula for our Hamiltonian, and it's sort of intimidating looking formula, but if you don't worry about it, it actually becomes nice. If you look at this term, it's a very simple term that gives you all the generic equations. And then there are some special corrections based off the 2 points where we do the transformation. So this is this extra term. Okay, so that's one result. And now I want to talk about the example of a discrete Painlevé equations of type A2. And for these equations, there are some nice forms that you can refer to as a canonical form of the equation. In particular, there's a very nice form of this Painlevé equation that was written by Sakai following work. Yeah. Huh? Okay, thank you. Sorry, thank you for the correction. Well, okay, I saw it in your paper and following Murata, but I don't. Did they write it in the same form? In the same form?
Yeah.
Okay, so that will be changed, but the equation will not be. There's the equation. Okay, so we think about this equation as a birational map of P1 cross P1 to itself with 8 parameters, and f and g are coordinates on P1 and P1. And the parameters change like this under the dynamics. And here's our equation. And if you look at the indeterminate points of this birational map and resolve these indeterminate points by blowing up, you get the surface xb, and the subscript here means that the way the surface is constructed depends on the values of the parameters and the coordinates of the points of the blow up. So you get a picture like this. For example, if you look at the first equation in the system, you see that when f is equal to minus g, you get a 0 in the denominator, and if you choose g to be minus b1, you get a 0 in the numerator, and this is 0 over 0 indeterminacy that gives you this point, and then you sort of get 8 points, and similar to the picture in the talk by Nalini this morning. And here is the picture indicating the blow-up, where for each point I now draw a line of exceptional divisor that is at the center of a blow-up. Okay. So then if you look at the Picard lattice of the surface, it decomposes. It's generated by the classes of lines HF and HG, the coordinate lines here, or rather their preimages, and also the exceptional divisors. And the anti-canonical divisor decomposes as a sum of 3 connected components, denote D1 and D2, these lines. And if you look at the self-intersection between these components, that's how you get the A2 affine Dynkin diagram. And the star here means that the lines not just intersect, but they also intersect at one point, which correspond to the difference case. And the generic one corresponds to multiplicative case. Okay. So then if you look at the orthogonal complement that is called the symmetry sublattice, has the following basis. And the symmetry type, if you look at this diagram, is of type E6, affine E6. And when you compute the action of our discrete Painlevé equation, that is now becoming an isomorphism between the surfaces xb and xb bar, you can explicitly see what it does, and you get just a shift in the sublattice by translation along a particular direction. Okay, so that's sort of the geometric picture of this Painlevé dynamics. And we try to recreate it using discrete Schlesinger transformations. So we start with a Fuchsian system that has only 3 poles, and we can make them 0, 1, and infinity. So in particular, there is no continuous Schlesinger deformations here. And this is a 3 by 3 system. And by zeroing one of the eigenvalues. There are no degeneracies. We have matrices of rank 2 sitting at the 2 finite points, and matrix of rank 3 sitting at infinity that we assume to be the diagonal matrix. So actually, it's convenient to write this using Fuchs relation. So these are 2 finite points, and the infinite one, there is a Riemann scheme and the Fuchs relation. And we look at the following transformation. So we decrease this eigenvalue by 1, increase this eigenvalue by 1, and keep everything else fixed. So, okay, I'll just show you some scary-looking equations. We write down this Hamiltonian function that gives dynamics that can be solved to give dynamics in the variables bc to the variables b bar, c bar. Don't pay any attention to these equations. If you want, you can really see them in the paper. But the point is, we need to now to introduce some coordinates. All of this is written in terms of eigen vectors, and now we need to put actual parameters. So we use the conjugation action to sort of make the matrix of B vectors an identity matrix, and use some extra action that we have there to normalize the fourth vector B. Then that uniquely determines the matrices C, pretty much. If you put the x and y parameters here, everything else can be written down in terms of x and y. So indeed, we have a two-dimensional system, and alpha and beta are some functions of x and y. Then we can actually explicitly find the evolution. So this is the evolution map, which looks pretty straightforward with one catch. And the catch is this alpha and beta that appears in these equations. So here's alpha. So that's the numerator, and that's the denominator. And then here's beta. So it's a bit of a mess. And this mess is, I think, partly due to the fact that the coordinates that we chose were not much to do with the dynamics that we wanted to study. And so we wanted to see if this map is related to this nice equation that I showed you previously. And again, we looked at the indeterminances of the map and resolved them using blow-up procedure. We started not with P1 cross P1, but with P2. And then we found the 9 points where you have to do the blow-up procedure to resolve indeterminances. And everything is computed explicitly. So we know the coordinates of all of those points. We were able to find the equation of this curve on which the points lie. And notice that before, the coordinates of the points were parametrized by these parameters b. And in our case, everything is parametrized by thetas and kappas. So the parameters of the actual Fuchsian system appear in this part of the story. And then to compare the dynamics, we'll look at these two pictures that describe the blow-up procedure. So this is sort of the standard example of the equation. And here is our example. And basically, we want to stare at the picture on the right and see a picture on the left. OK? And to do that, you look for -2 curves. Because this is a special -2 curve that can be identified with this one. Here's a -2 curve that I think is identified with this. And this guy is identified with this. And the rest follows. OK. So yeah. So D0, D1, and D2 that we had previously, we recognize as this on our picture. And what that means is we can introduce a new coordinate f that corresponds to the pencil of curves going through the point E1, and the new coordinate g that corresponds to the pencil of curves going through the point E2, and then use the rest of it to sort of do the small adjustment of the parameters. More specifically, we want the points P5 and P6 to be on the line f equals infinity, 7 and 8 to be on the line g equal to infinity, and the other 4 points to be on the line f plus g equal to 0 to sort of completely match the picture on the left. So if we look at the pencil HF, these are all lines passing through the point P1. So This is a generic equation of a line and the condition that it goes to this point. So in other words, you can write it like this with some parameter beta. This is a projective coordinate, and then you sort of decide how to go from the projective to the actual coordinate to satisfy these conditions. Similarly for hg, so we get the projective coordinates f and g, and then if you look at the coordinates of these points in this projective way, you see the coordinates are -1, 0, 1, 0. So to put these points at infinity, for f, we need to divide by this term, and this is what we do. And similarly for g, to get infinities, we choose the parameter alpha to be -1. It's convenient to choose beta to be this. And we get this change of coordinates. Then the conic factors, and then we want other 4 points to be on this line. They are on this line, sorry. We want the equation of the line to be f plus g equal to 0. So that requires us to do some extra adjustments. But then with these coordinates, we completely restore the picture of the Okamoto space in the model example that we want to connect to. And more than that, because of this, we have an explicit matching of the parameters b that appear in this standard example with the parameters theta and kappa that come from our Fuchsian system. So then what we can do is we can actually go back to the Riemann scheme and see what kind of dynamics we have. This is our dynamics, and this is the dynamics that corresponds to the canonical example. So the point here is then that even though that we have equations of the same type, the equations are not equivalent. They're infinitely many discrete Painlevé equations the same type, because you can choose different translations in the symmetry sublattice, as you can see here, and very explicitly here. So this is the action of elementary Schlesinger transformation, and this is the matching action of the standard example. So you can think about one going sort of horizontally and the other one going diagonally. That's a nice analogy. But then what you can do is you can sort of make a step and then turn, and make a step and then turn, and you then get the standard Painlevé dynamics from this elementary Schlesinger transformations, and that involves some change of variables and some randomizations, but in fact we can verify this by mathematically essentially typing this formula in Mathematica, and it says yes after a couple of hours. Okay, so I'll stop here, and here are some references. In particular, in this recent preprint by Carster and Tekinava, they talk a lot about doing this geometric analysis of Okamoto space of initial conditions. There are a lot of details there, and our preprint is also on archive. Thank you very much.
Okay, any questions? So, if not, let's thank our speaker one more time.